Hello, my name is Thomas. So today I'm gonna be doing the project coin tossing by Clark Willman, Computer Science 110. Okay. So the first thing that we need to do is we import the random from random, import random, and defining the random coin tossing function with the probability pH, you can see here, using boolean if random smaller or equal to pH probability of head, return 1. So return 1 is head, and else return 0 is tail. And afterwards we define the function of coin tossing with the n toss. N toss means n times, and the probability stimulated probability, and so you can see based on the accumulation nh equal to 0, so nh plus n equal to ct with a pH, and using the for loop range n is times of tossing coin, and it will accumulate the nh with the n times, and after that we return nh. Moving on to sorry, the rest I will show you later on. Okay, so moving on to 48 cases of stimulated probability. I'm sorry, just okay, stimulated probability. Okay, stimulated probability. So the way that I figured out is instead of defining the two CT and toss and m times, and the probability of CT and toss and m times, I combining them together in one function by using list accumulation, or you can use dictionary to use, because these accumulation, list accumulation and dictionary are really helpful for you to get the effective result, and to have you a lot is really useful. So first thing that I do is writing the coin tossing file using nested loop in order to stimulate the tossing coin with n times 5, 10, 20, 50 repeatedly with m is 1000 multiply n, 1000 multiply 5, 10,000 multiply n, and 100,000 multiply n, with the pH probability of the tossing coin is 0.5, 0.52, 0.55, and 0.6. So we appending the number of head to 0. What's that? Okay. Depending to number to 0, because to get right here. So you using the different for loop and list accumulation or dictionary because of mixing number. So the mixing number is like when you do for example, from 5 to 10,000 multiply n and 0.55. You can see, oh sorry, let's make 10. Okay, so you can see some point of like from 1 to 10, from 10 to 20. 20 is like from 13 to 20 because of missing number that we need to so because of that error we need to create the dictionary and create a list to get that number. So you can see, so toss ACOM I set to 0, probability of A come, I set to 0. So I create the dictionary for NH in range N -1 and -1, D and H to 0. So for Thomas in range M, we can see M right here, D and H plus and equal to N. To 1, because when we this is for some of all probability is like it will divide by 0 if we don't get it to 1. So toss A come, get it to 1 to prevent dividing by 0. So let me open the okay, I'm sorry. Let me open the code. Okay, right on. Oh. Okay, the code is right here. So the rest of the code that we can see is so I use nested loop to do everything. It's pretty good and it's really helpful for us to get the 48 cases. So where was I? Okay, so we are gonna be doing flipping the coin n times. You can see for an H in range M, H is head, so equal to CT and toss, right here, and CT and toss inside the nested loop. So and we append the LH to 1 plus and equal to 1. So afterwards we're gonna be doing for an H in range N plus 1. So in this point we got a really important contribution, that is L and H divide M contributes the main purpose of stimulating the probability. I mean, this point, this is the stimulated probability. Afterward that we put all the thing inside the table and write down, so we can see using format. And yep, so as the end we can see for an H in range N plus 1, probability H, D and H we can see divide toss A come. So probability of A come plus and equal to probability H. So we can get the sum of all probabilities is probability A come. Okay, so moving on to the second part is all the function that you gave us, and we need to modify it a little bit and to get the true results. So defining the factorial using the accumulation. So accum multiplied equal to I with the n parameter, following the formula of n factorial divide m factorial n minus m factorial. So num is factorial n, as you can see. So denom 1 factorial m, we call it. So denom 2 factorial n minus m. Denom 1 multiply denom 2, and return, and return num divide the total denom right here. Okay, so we afterward that we define the probability of head with N and H and PH. So what are they? So they are NH, the heads are made with a coin having a probability of head, PH, and N times. Okay, so with the so right now we are doing the 48 cases of predicted probability error and relative error. So we're doing exactly the same thing with stimulated probability. So we define the task to write down the name error file, doing exactly the same thing with predicted probability. But hold on a second, we can see the for and h in range a little bit different. So let me get straight into it. So we already done that. So we calculating error and relative error with absolute numbers, error by formulas. Error equal to stimulated minus predicted. We're using absolute number L and H minus probability of head N and H PH that we listed above, which is predicted. Remember, this is predicted and this is stimulated, because some people like thinking they are the same thing and they have no idea what are they doing. So pretty common circumstances. Relative error, using formula is error divides predicted probability and multiply 100, getting the percentage. So I don't want the percentage is negative. Sorry, in negative, so it's pretty kind of nonsense. So I need to get the absolute number, error divide probability of head N and H PH, multiply 100. Yep, that is the formula, and doing exactly the same way to get the sum of the all probabilities. Okay, so the output is, you can see I get a small part, but right now I will show you I will show you how to test it. So because okay, so this is to file, get the calculator. Okay, so let's test it. So 9, okay, 0.0929, okay, right. Okay, exactly the same number, but it's absolute number, so yeah, it's a little bit different. And divided by predicted probability. Yep, you can see 100. Yep, so after this test that we can see everything is correct, seem correct. Yep. And moving on to the last thing is searching a coin to be fair or not using the above results. I'm taking this to test. So let me read this. So the practical problem of checking whether a coin toss is fair might be considered as easily solved by performing a sufficiently large number of trials. So it might be necessary to test experimentally whether the coin is in fact fair. That is, whether the probability of the coin falling on either side when it is tossed, approximately 50%. Let's have a check. So you can see some kind of coin, approximately 50% is gonna be good. It's gonna be fair coin. So it's not. It's predicted, stimulated. Yeah, it's right here a little bit. It's pretty good. It's pretty good, but not a fair task. So after that, we can compare to each number. So thank you for watching and appreciate that.